Hi everyone, so this is the fourth video on the Alkene Notes video series, and this one we're going to be talking about the class of reactions that fall under the halogenation, halohydration, and haloalkoxylation. So for this first one, we're going to be looking at just the halogenation. So we're looking for a reaction between an alkene and something like Br2 or Cl2. And what we'll see is that in this reaction, we end up with the anti-addition of two bromines or two chlorines, and we get a pair of compounds here where one of the bromines is going to be dashed and the other one wedged. All right, so for the mechanism, the first step of this reaction is that we have that alkene performs that nucleophilic attack on the bromine. And the arrows for this one kind of look a little bit funny, so I'm going to draw them out. We have that the electrons from the electron go to one bromine, while at the same time, a pair of electrons from the bromine go to that carbon as well. And then this electron pair between the two bromines breaks, and we end up giving those electrons to that single bromine on the right. And so in this reaction, we form this bridged structure that looks something like this, where we have that single bromine ends up being bound to both carbons at the same time, and we end up with that bromine ion as well. And so here I'm actually going to draw both products that are formed in this step because this attack can come from either side of that alkene. And so we have one pair of, or half of the reaction will end up with that bridged polonium ion being wedged and the other half being dashed. And so we end up with a mixture of stereoisomers here. One thing to note is that this reaction does not go through a carbocation intermediate like those other reactions that we did. And so the stereochemistry in the products comes entirely from this structure that's formed here. And the structure is called a bridged polonium ion, where we have this three-member ring with a positive charge on the halogen. All right, so now that we formed those, and I'm going to copy those over here. So we have those two intermediates, and then we also have a leftover bromine from that first step. And so in the second step, that bromine can come in and attack that ring structure. So we know that three-membered rings are highly strained, and so they want to break. And that bromine also has a positive charge. It doesn't want this positive charge, it wants to get rid of it. So it wants to swing open and form just a regular bond to a single bromine. And so for this, we get attack at the more substituted position. And so here I'm going to underline more substituted. This is different than epoxides, where if you just have an oxygen in a three-membered ring, it usually attacks at the less substituted. So if you've already covered epoxides, make sure that you're not confusing the position where it attacks. In these reactions, it happens at the more substitute position. So I'll draw it for both. And so once we get that attack at the more substituted position, we end up swinging open that bromine, which stays dashed. And what we get in the on the other carbon is inversion of stereochemistry. So that bromine that comes in has to come in from the opposite side of the ring. And so we end up with a bromine that is wedged here. And then that methyl group ends up being dashed. And so we can see that in this product, the bromines are anti. So they were added anti to that carbon-carbon bond. And so we can draw the other product forms from the second reagent where that bottom bromine ends up being wedged because it was wedged in that bridged polonium structure. The one that came in is going to be dashed, and then that methyl group is going to be wedged. All right, so here we formed a pair of enantiomers. It's not necessarily always going to be an enantiomer because you might have another stereogenic center where you would end up with a pair of diastereomers. And so if you're not sure if it is a pair of enantiomers or not, I would just suggest drawing out both products. All right, so if we compare this to the reactions that we covered in the previous video, the key difference is that we don't go through a carbocation intermediate. So we don't have to look for rearrangements at any point in this reaction. And then the other key feature of this is that the products end up having defined stereochemistry. based off of the anti-addition of the two halogens. All right, so that finishes halogenation. Next, we're going to move on to halohydration. And what we'll see is that this reaction is very, very similar, especially for the first step. But the key difference is that instead of adding two bromines or two chlorines, we're adding a single bromine or a single chlorine. And then the other thing that we're adding is this going to be OH from the water that's in our reagent mixture. And so we end up forming what's called a halohydrin, which is where you have that OH and the halogen right next to each other. All right, so let's get started with this. So that first step is going to be identical. I'm going to just copy this over from over here. We're forming the exact same first intermediate here, where we have that alkene attacks the bromine and forms that bridged polonium structure. Our first step is not going to change. We also end up forming that bromine here. And so some people ask, why don't we just form the same exact products as in the previous mechanism? But the key difference between this one and the previous one is that we have a high concentration of water. And so because we have a high concentration of water, the favored attack is from that water instead of a bromine. So we have a lot of water in the solution, it's available to attack. And so in that second step, instead of having the bromine come in, we have a water molecule come in. And so we can show this as that OH2 attacking at the more substituted position, swinging open that ring. And so we end up adding on OH2. And similar to the previous mechanism, we're adding on that OH2 anti to the starting bridged polonium structure. And what we'll notice is that similar to the hydration reaction from the previous video, we end up having a charge on that OH2. And so in our last step of the reaction, we're going to deprotonate that OH2 to end up back at the OH. And for this, we can just use a normal water molecule. As a reminder, if we're just in regular water, we don't really just have free-floating OH around. And so for this, we would just use a regular water molecule for that acid-base reaction where we deprotonate that hydrogen and give those electrons to the oxygen. And we end up with our final products where we have an OH that's wedged and that bromine. And so similar to that reaction that we just did above, we end up with the anti-addition of the OH and the bromine overall. And similar to the other one, we also didn't go through a carbocation intermediate, so we don't have to worry about rearrangements in this one. All right, so now we have our two reactions, one in which we added two halogens and formed anti-addition of two bromines. And this one we added anti-addition of OH and a bromine. And so this last one is going to be a combination of those two, but instead of an OH, we're adding on an OR group. And so instead of doing this reaction in water, we can do this reaction in an alcohol like methanol. And so altogether, we end up adding on an OR group. And our R group here is just the methyl. And so we can see that we added on OME. Now, underline it here to kind of show where it's coming from. And very similar to this other one, it's going to be basically the exact same. So similar to this one, I'm going to just copy over this mechanism for step one here. Not going to change anything at that. However, in the second step, what we're going to see is that we're going to have the methanol attack instead of the water. So I'll draw in that methanol. For both of these, and then show that the electrons from the oxygen attack again at the more substituted position. And swing open that ring. And for this one, we don't really care about that bromine because we're doing this reaction in the methanol. There's a lot more methanol around, and so it's much more likely for methanol to come in and attack. And if we recall from the previous video where we talked about hydroalkoxylation, we remember that we had that positive charge end up on that oxygen. And this is very similar to what we just did with the water, where we end up having OH2 instead of an OH. And so our last step for step 3 is going to involve deprotonating that methanol. And for that, we can use another methanol molecule to deprotonate them. And some classes will just use that bromine that you formed in step 1. So your instructor might be doing that, but either one is fine. And so we have these electrons from the oxygen come in, deprotonate, same thing here, and give those electrons to the oxygen. And altogether, very similar to all the other ones, we end up adding a OR group in the anti with that halogen. And so if we compare all of these reactions, the unifying feature across all 3 of these is that we're adding in anti-addition of a halogen and something else, and that we're going through that bridged polonium ion, and that the nucleophilic attack comes at the more substituted carbon. So those are the key features to pay attention to for this reaction. And the last thing I want to mention is that this last reaction, a lot of classes they like to throw in a intramolecular example. And so that OH attack can come from something that's already in the molecule to help cyclize the molecule. And so I have a few practice problems that have a few of those intramolecular reactions. So in the next video, I'll have those practice problem answer key. All right, that wraps up this one.